Okay, good afternoon again. Officially, I would like to start the content today. In my last class, I talk about uh, the briefing, right? It likes what are the CLOs, what are the PLOs, how I am going to assess uh, for this course, and what are the time durations I am planning to take the topics. Okay, according to the weeks. Anyway, so this part actually I already explained a little bit. Okay, so hold on 1 minute. Okay, so as I know that you already just gone through the fluid one, so you should have the knowledge of these kinds of thing. Okay, so this is the flow within the pipe. Okay, it means like if you have a pipe for a particular length. Okay, so for an example, maybe L, and you are considering the flow, undisturbed flow, that is the, we call this US free stream flow, or you can also consider, sorry, U infinity, all are okay. So if you consider the flow is coming from the left and you try to measure the velocity profile along the cross section, okay, so how you are going to face it. So last time I said that about the real fluid and idle fluid, right? So in case of idle fluid, if you consider any cross section, you should have these kinds of profile. It means all the velocity should be same. Okay, if you move away from the center line, going upward or downward, you will get the same velocity. So this is the basics. Okay, however, in reality, it's not like that. So reality, if you want to go towards the reality, so if you consider the different cross sections, you are moving away from the source or the inlet, so you will get the different types of profile. Okay, so initially at the beginning of the profile, I mean at the entrance of the pipe, so that will be the free stream velocity, right? So if you consider the cross section here, so you will get the same. That is the input here. So after that, as I said, so due to have the friction, because it's a real fluid, and in case of real fluid has friction, we call this like viscous flow, right? Viscous flow, or we call this rotational flow. So in case of viscous flow, the flow that is attached with the solid surface here is actually will have no velocity. Okay, so the layer of the fluid that is completely attached or very close to the surface here, or we call this wall, that will have zero velocity. So if you have zero velocity, and then at the center point we'll have the maximum velocity, because the influence of the wall is minimum, or you can say that negligible here. Okay, so the influence of wall is maximum at the contact point, and the influence of the wall is minimum at the center line. So if you consider the velocity 0 and then maximum, so how it could be? So normally it looks like parabolic shape. Okay, so but the shape keeps changing, okay, until it's considered or until it get the developed form, fully developed form. So these envelopes are actually called the velocity profile. Okay, and if you see here, this flow is, we call this the flow is for the viscous region, or we call this boundary layer part. Okay, so this say that the velocity for boundary layer. Okay, so it means like the velocity boundary layer effect is much higher here, so we call this region is actually belongs to the boundary layer. It means that the velocity will keep changing. Okay, and if you consider this profile, the profile or the zone where the velocity change is not that much, that is close to the center line here. So initially the zone that is where the velocity change is negligible, that is actually bigger, because it's just started, right? And so you can see that the profile, this one that separate the real and ideal zone, that is actually gradually reducing. So initially all are actually ideal, right? So it means that you just the fluid just enter into the pipe, and the velocity distribution is all same, whatever position you consider here. But later on, if you gradually move towards the length or along the length of the pipe, so this zone, the separation zone, gradually reduce. It means like the zone that is belongs to the real part or boundary layer part is gradually increasing, and the real part gradually, ideal part will be gradually decreasing. So this separation line will be gradually reducing, and at the end here you can see this, there is no more ideal part. Ideal part means is actually there is no ideal part, but ideal part means, I mean that where the velocity change is constant. Okay, so within this zone all velocity is same. So here the velocity is same. Then is here velocity same. After that there is no influence of that. That means the full part is for real fluid. So it means that is fully developed zone. So whenever this separation curve ends, then after that you will get the fully developed velocity profile. That is the thing. Okay, so this one is the, we call this hydrodynamics entrance zone. It means that the position is still in the transient state or transition stage from before getting the developed form. So this is the fully developed. So we have the skip changing part, so we will call this hydrodynamic entrance zone. Okay, so this is the basic thing, and then you already have the knowledge of laminar flow, and then transition flow, turbulent flow. So this one we call this, actually we can do experiment, we call this Reynolds experiment, because it's actually we separate this turbulent, transition and laminar flow by the Reynolds number. Okay, so I think you already know these things. So anyway, I will again go through those part. So basically what we do here, we have this pipe. It could be horizontally placed, it could be vertically placed, should be okay, but we have the die here, and we consider the die, and we try to trace the die part. Okay, so when the flow inside the flow is very normal or very slow or moderate, so we can actually separate this flow gradually, like very straight line, it will go like this. So it means that it's separated. Okay, we call that one is actually laminar flow. It means the flow is separated. You can actually visually distinguish the layer of the die that is separated by you can actually distinguish the layer or the streamline of the die from the flow. So later on, if you gradually increase the flow rate, we call this flow rate Q. So that is Q is the rate of flow. Okay? Q is equal to AV. I think you already know these things. V is the velocity, A is the cross-sectional area. That is very important formula that we always use. Q is equal to AV, and M dot, it means the mass flow rate, is equal to rho AV. You should know all these formulas, okay, from fluid 1. If you forgot, then you can write it down. This is the mass flow rate, this is the flow rate. Okay, so in this case what will happen, so that's how I said that by manipulating the flow rate Q, you can actually distinguish these three types of flow. Okay, so this is the problem that I will solve later on. So in this part, this is just a brief explanation. Okay, so laminar, turbulent, transition flow. Then we have what kind of boundary layer. So you will get into know in details of those things. So here introduction in this case. So what we are going to know here. So we have this feature of external flow, that is we call this laminar or turbulent or transition flow. Fundamental of boundary layer, including laminar, transition and turbulent areas. Okay, so how the boundary layer will change. These are the content for real part, because we will use we will start the real part first. So real fluid. So in this case, as I said, you will get into know the external flows, and then you will get into know about the boundary layer. We will try to find out how the boundary layer will change, including laminar, transition and turbulent areas. We have some boundary layer parameters for flow past a flat plate. Okay, so we will explain few things or few parameters that you need to know. Okay, description of the boundary layer separation, how the boundary layer is separated, lift and drag force, and Navier-Stokes equation. So these things I will explain. one by one. Okay, and then the latest one is the various aspects of flow around the bodies. It means like flow around the circular cylinder or half cylinder or a sphere, those type of thing. So these are actually again the content. Okay, so now the basic thing comes that you need to distinguish the ideal fluid and real fluid. So, but in the first class I already said that ideal fluid is that fluid which has no friction or viscous. We call this inviscid, where the flow particle actually, or fluid particle actually, we have a irrotational flow. It means there is no rotation on it. It can slip from on the top of it. Okay, so we have the slip condition. So it can slip. So if it can slip, it means there is no friction. Okay. On the other hand, we have the real fluid, that is viscous flow. In this case, we will have the shear force. Okay. So normally, when you immerse the fluid or any what can I say, solid body inside the fluid, we will have two different types of force. Okay. One is pressure force. Remember. Another one is shear force. It means that if you have the submerged body, any submerged body, so some force will act perpendicular to the surface. So the force that is acting perpendicular surface is known as pressure force. We call this fluid pressure. Okay, and another force that will act tangential to the surface. It means against the motion of the solid body. So one will be perpendicular, another one will be tangential. So perpendicular force is actually pressure force, fluid force, and the tangential force is actually the shear force. This shear force is actually the friction. Okay, so you have to overcome it. So it means that in case of ship, okay, so we have, when we have the resistance, it has several components that I will talk again later. So it has the frictional resistance, it has the wave making resistance. Okay, so mainly is two basic part. So frictional resistance actually is coming from the shear force. Okay, so it means that you need to know the boundary layer. So because it's a real fluid, so it actually poses some resistance against the motion of the solid body. In our case, if it is a ship, so we need to overcome the resistance. That resistance is actually frictional resistance, and this resistance is due to the shear force. That is the force that is acting tangential to the surface. Okay, so what are the difference of ideal fluid and real fluid? So some part is actually, I deliver my lecture for understanding, but you cannot explain these things in this way if you want to get marks, right? So somehow you need to be in some particular format you need to follow. So that's why the lecture materials are given just for following. But for understanding, my lecture would be enough. Okay. So you can see that maybe the linguistic way is presented in a different way, but the meaning is same. So ideal fluid is a fluid with no friction. Okay, that's good. So I go for the ideal fluid first. Okay, then also referred to as inviscid flow. You already know that inviscid flow is that flow we have where we don't have any viscosity, right? Zero viscosity. We call this non-viscous. You can call this inviscid. Same meaning. Then internal forces at any section within there are normal pressure. So in this case, if you have the ideal fluid, you will only experience the pressure force that is normal to the surface. We don't have any force that is acting tangential to the surface because it's an ideal fluid. Application: many flows approximate frictionless flow away from the solid boundaries. So there are many flows we consider that is ideal fluid, so we don't have any friction. So there we can use the ideal fluid part, or we can consider the concept of ideal fluid. And the flow is also known as, remember, potential flow. So potential flow is the flow for ideal fluid. Okay, so somehow I can find the cursor. Okay, so what I say, that potential flow. So potential flow means the flow of an ideal fluid. So how about the real fluid? So we will have the tangential part, right? Tangential force or the shear force always develop when there is a motion of the fluid. So if you are moving within or inside a real fluid, of course you will get two different types of force. One is pressure force, another one is tangential force, that is the shear force. Yeah. So fluid friction will be created, and then the shear force opposes the motion of one particle past another. Okay, so it means that we have the rotational flow. So this is irrotational. In case of irrotational flow, remember that if there is a layer of fluid like this, another layer of fluid will pass on the top of it or along it, but it can slip. We have the slip conditions. It can slip. Okay, if you, it means like if you have the grease, it feels like grease, so there is no friction. It can slip like on the top of it. On the other hand, in case of a real fluid, it cannot slip. We have the non-slip condition. Okay, so it means that you cannot slip. You need to you need to pass on the top of another layer. You must overcome the resistance. So it has the resistance. So frictional force gives rise to the fluid property called viscosity. So that's why we have the viscosity. The term viscosity, it comes because we have different types of fluid, and each fluid has its own different types of frictions. In order to measure the frictions, we have the term viscosity. So we is non-viscous, that is no friction. We have viscous, which one is more viscous, which is less viscous. So we can define, or we can separate the different types of fluid, real fluid, based on their this viscosity part. Okay, so viscosity is actually a measure of the fluid resistance, okay, to an angular deformation. It means that if you want to you want to pass through it into a fluid, you must overcome the resistance. It's a kind of measuring the measure of the fluid resistance, actually, the viscosity. So more viscous fluid means it gives more resistance. Okay, so we have the viscous flow. This is the basic thing that you probably you already know. In 1883, Reynolds, an English investigator, observed the flow of water through a glass pipe. I'm just reading, okay? Then I will explain. A glass pipe which drained a container water as somewhat his. So it means like it has some arrangement like this. It has a container, it's full of fluid, and it has some outlet. It can go out, and then there is a valve. He can control the flow rate with this valve. Okay, so he first filled the tank with the drain close. So he just closed the valve and filled the water, and then when it came into rest, he also there is a process of injecting the dye. So this is, we call this Reynolds apparatus. So what will happen? These things you already know. After opening the drain valve, okay, he found that the flow are streamlines and visualized by the stream of ink. So you want to measure, or you want to analyze the flow pattern by injecting the dye. Okay, so streamlines were straight. Of course, when the flow is very low, it means the streamlines were straight and parallel in the first segment of the pipe. Just downstream flow is the entrance, and the flow velocity near the pipe, I will explain, okay, just I read and then explain. I will flow, and the flow velocity near the pipe wall was less than that near the axis of the pipe. It means that it's trying to explain the velocity profile. Okay, so you know that along the center line the velocity is maximum. Here the center along the close to the wall the velocity is minimum. So he said that the flow velocity near the pipe wall has less. So here the velocity, here the velocity is less, and if you compare, if you go close to the center line, you will have the more velocity here, right? That is the velocity profile. So he observed these things through the experiment. So he inject the dye, and he tried to follow up that how the velocity distribution here. So he will feel that this dye is moving faster here, is little bit slower and slower. So this one is you can get in the fully developed zone. It means in case of turbulence zone. I will show you the video later on. So a streamline eventually become irregular as the flow progress further along the pipe. This first happen near the mouth of the pipe, for flow near this wall, and further downstream of flow along the pipe. It means that, so yeah, the story is, so if you have the pipe, okay, so initially first portion here the flow is actually laminar. It means you can actually distinguish the flow. Okay, then after that is gradually become turbulent, and then you have the mix up. So it means that along the close to the entrance, so here is the laminar flow, then some part will be transition flow, and then after that you will get the turbulent flow. Okay, and he also mentioned that then when he measure, or when he increase the Q value, it means the flow rate, so the region here, the laminar region is actually gradually reduced. Okay, this part is actually reduced. If you have Q is if you increase the Q, it means if you increase the flow rate, then you will have very small part that is laminar. After that, you cannot distinguish the dye because it will mix up with the flow. Okay, so the region until where you can actually visually distinguish the layer, I mean distinguish the dye, that is the laminar. Okay, then we will have the vorticity or transition, and then after that completely mix up. Okay, so that's how we can define the laminar, transition, and turbulent flow, and it depends on the Reynolds number. Okay, so that is Reynolds number means if you increase the Q, actually we can actually manipulate the Reynolds number. And if you also manipulate the Q, you can actually control the length of the laminar flow. And so if you have high flow velocity or high flow rate, then the region for the laminar flow is very small. Okay, so these are the findings of him. So you can read all the things. So he explained in this way. Just try to spend some time and try to read because I think these statements are quoted from some books. Okay, so further he observed that he kept the valve nearly closed, the above development process and vesseless abrupt. The flow progressed further before the interflow became irregular. So in short, like that, these are books form of a way of explaining. So in short, it means that at the beginning you can distinguish the layer of the dye, so that is laminar, and after if you move more forward, you will gradually the flow become irregular. It means like you have the vorticity or turbulence, and your flow will become turbulent. Okay, and then the dye will be mixed up with the other flows. You cannot distinguish, and you can change the length. Here you can see that if the flow velocity was higher, then the whole process took place in a shorter length of phase. So whole process means the turbulence. Okay, so you will get the turbulence phase very quickly if you increase the flow velocity. Okay, so I just open one video for you. You can see 1 minute. Okay. This is Reynolds apparatus. Okay. So he's first fill the reservoir, close the valve, and then adjust the small flow rate. And he will also open the dye valve. So you can see the dye. It takes some time to get the stabilized form, so it's just started, so it will take some time to become stable. Then you will see, literally see the flow. I mean, the dye can go along the flow. It's gradually developing. It will become steady state. Okay. You need to give time to stabilize the flow. Now you can see, you can just observe the laminar flow. We call this laminar because you can see literally distinguish the flow, right? If you maintain this low velocity, then you will have, it means the laminar length is bigger than the pipe length. So along the whole length of the pipe, you can experience the laminar flow. So now you increase, you will experience the transition flow. Transition flow is in between, like it's not mixing and mixing, something like that. Is you will have the vorticity or turbulence, okay, but still you can distinguish, right? So this one is a transition flow. So you can see that the laminar one very close to the entrance. Now it's turbulence, so it is totally mixing up. Okay, so there is no existing of flow streamline for the dies. That is the basic sense. I think you already know all these things. Okay, so I will share this video later on. I will upload it later. So what is the conclusion after this experiment? It means that by repeating the experiment with other fluids, so we can actually have some conclusion. Okay, we found that there is a number. Okay, that is a ratio of viscous inertia force and the viscous force. So we have two different types of force here. This one is inertia, and we have the viscosity. Okay, so this is the ratio. If you consider this ratio, so this inertia force divided by viscous force, we can express this ratio as a number. We call this Reynolds number. Okay, and we found this ratio is, it means the Reynolds number actually we can use it to define the laminar transition and turbulent flow. Okay, so that is his findings. So that's why we, according to his name, we call this Reynolds number. That is very important. So Reynolds discovered that the similar phenomena will be observed when the flow dimension parameter had the constant value. So it means that you consider any flow is okay, but if the Rn value, it means the ratio of inertia force and the viscous force is same, you will experience the same scenario again and again. So it means that, of course, is related with the Reynolds number. If you change the Reynolds number, the scenario will be changed, but that scenario will be belongs to or corresponding to that particular Reynolds number. Okay, so V is the velocity, flow velocity, D is the diameter of the pipe. It can be a length, is a singular dimension. Okay, so it could be D, it could be L. It means the unit of mass. Meter. And mu is the kinematic viscosity. So as I said, the Reynolds number, sometimes it may say that what is Reynolds number. So this actually physically is a ratio of inertia forces and the viscous force. And the viscous force are most important. Therefore, the Reynolds number, it means that if it is very big viscous, so Reynolds number is small. Okay. So we have the relationship. Okay, so mu is higher, the Reynolds number is low. If mu is low, then the Reynolds number is high. Okay, so we have two different form of Reynolds number. You already know these things. So Reynolds number can be represented by Vd, small d or capital D, or you can also write L by mu. And on the other hand, we have the rho Vd divided by mu. Okay, so one is mu, one is nu. So this one is kinematic viscosity, and this one is the mu is the dynamic viscosity. So how is different? So dynamic is also known as absolute viscosity, is a measurement of the fluid internal resistance to flow. Okay, this is actually measure of the capacity to resist the motion, is a measurement of the fluid internal resistance to flow. On the other hand, kinematic viscosity is actually the ratio, okay, the ratio of the dynamic viscosity to the density. So mainly is the absolute velocity or absolute viscosity is this is the main one, mu. Okay, so these things you already know. So probably if they ask you like Reynolds number, I don't think they already asked. I think Reynolds number you should have the knowledge. Okay, so so I just continue. Okay, then I will ask the questions or will ask your feedback. So now you already know the Reynolds number. So rho VL by mu or rho VD divided by nu. So okay, so you know the dynamic viscosity, you know the kinematic viscosity. If you don't know, you can also refer back here. Okay, so next thing is boundary layer. Okay, this is the topic where we will spend more time, because Reynolds number is also you are familiar with. Reynolds experiment, this is also not new for you. Boundary layer, I think you also know, but we need to know more on that. Okay, so what is boundary layer? In short, okay, I want to explain in short. So short is, as I said, if you have, this one is a stationary plate, okay, and we have the moving plate. The plate is moving. u infinity. You can consider this situation, or you can also consider, maybe better we consider the flow around inside the pipe. Okay, you have the pipe and the flow is here. So if the flow is u infinity, as I said, that the flow, a layer of fluid will be attached with the wall. Okay, so in this case, your velocity profile, if you draw, this one should be 0. Okay, but this should not be 0, right? So you should have u infinity, but at this point you will have 0. On the other hand, if you move towards the center line, I try to zoom it out. So gradually your velocity will increase, will increase, will increase. Okay, so it means that your velocity is not uniform. Okay, it's gradually increasing. And how long it will increase? Until it reaches u infinity. So you have 0, gradually it will increase. So in case of Newtonian fluid, so this increment or velocity gradient is actually linear. Okay, better I open the Word file on noise fix. Okay, so why I cannot draw straight? Because it's my digital board is not properly functioning. Anyway, so the thing is, I want to draw like this. Okay, so this is the wall. This is the wall, and this I'm drawing the velocity profile. You have the flow. We are zooming it. Okay, this is actually very small. So this one is u infinity, and this is 0. Velocity profile is gradually increasing. So this one is how much? So for an example, this is small u. Okay, this is small u. All this is r small u. Is changing with the time. Not with the time, sorry, it's changing with the distance. So the gradient will be del u by del y. So sometimes it's changing very quickly. In case of turbulent flow, du by dy, it means velocity gradient is high in case of turbulent flow. Laminar flow, we have the velocity gradient is little bit less. Okay, so it's u changing but not abruptly. But in case of turbulent flow, the u will change abruptly or very quickly. So anyway, our concern is, for an example, this one is u infinity, is attained its maximum value, right? The velocity cannot be bigger or larger than the free stream velocity. So here you can see that at this portion, if you consider, so we have a loss of flow, right? So everywhere should u infinity should have u infinity, but here is u infinity is okay, but here we don't have u infinity. So here is the reduction of the flow is how much here? Reduction of the flow will be u infinity minus u, right? So also you can have the reduction of flow along this distance, right? So everywhere we have a loss of flow. So if you have the loss of flow, so you will not get the flow rate that you are expecting, or you will not get the result that you are expecting, because the flow is not there. So you have a loss of flow. Okay, so here we have a distance, for example, is delta. Okay, and if this u is 99%, 0.99 of u infinity, if you consider a distance from the wall to a point where the velocity is 99% of the free stream velocity, so that distance is known as boundary layer thickness. Okay, we call this boundary layer thickness. It means the thickness of the boundary layer, and the layer, it means, what is a boundary layer? Boundary layer is the layer where we have a loss of flow. Okay, so if we go to read theoretically how it's defined, the condition of zero fluid velocity at the solid surface is referred to as no slip, and the layer of fluid between the surface and the free stream fluid is termed as boundary layer. This is what can I say, in bookish way to explain. It means, as I said, this we are considering the real fluid, that is no slip condition. No slip means there's a velocity is 0. Okay, so slip, if you have the slip condition, it can slip on the top of it, so it means that there will be no resistance. So if we have the 0 velocity, it means we have the no slip condition. In case of real fluid, we have the velocity is 0, that is close or where that is attached with the solid surface. And we also have, if you move towards the center line, of if you are moving away from the wall, the velocity will be gradually increasing. So there will be a layer of fluid where the velocity is always less than the fluid surface, I mean the free stream velocity. That layer is known as boundary layer. So that is the same thing. Okay, if you can explain in that way, it should be okay. So the condition of 0 fluid velocity at the solid surface is referred to as 0 velocity, no slip condition. It means velocity is 0, and the layer of fluid between the surface, it means from 0 to free stream velocity, is known as boundary layer. Is actually not free stream velocity, is actually 99%, 0.99 of u infinity. Okay, but you can actually say that free stream fluid. So it considered the boundary layer is formed on the infinite long plate along which the flow is viscous, incompressible, as shown in figure 1. So it said that, as I said, you can consider the flow inside the pipe, or you can consider this is the stationary wall. I mean that you have the flat plate and the flow is streaming flow. We consider the flow stream. Okay, maybe using the u infinity. So we have the free stream, so all velocity are same. Then you can see we have the layer. This one, if you consider this point, so at this point u is equal to 99 u infinity. So you can see that the layer is actually gradually increasing, right? So this is actually boundary layer. For laminar is here, but for turbulent is bigger. Okay, so the simplified particle flow within the boundary layer consists of laminar, transition, and turbulent. It means you have the length of, for example, the length of the plate is L. Okay, so at the beginning we will have laminar flow. If you are moving away, we will have the transition flow, and at the far end we will have the turbulent. Okay, so this is the same as I said for during the Reynolds experiment apparatus. So in case of laminar layer, so the gradient is maybe it means the change is not that much. Okay, so it means that it can attain the 99% very quickly. If you have the turbulent, then it takes time. It means the velocity gradient is gradually moving like this. So the layer of the fluid is higher in case of turbulent, and it will develop. Okay, if you move away from the leading edge, it will gradually develop. So this is the condition. Okay, in details. Sometimes we ask the students what is the boundary layer and show the sketch or draw the sketch. Okay, so you can draw this one, or this one should be okay. So this is a free stream velocity. We have the Reynolds. Okay, so you can also understand why these are actually getting from laminar to transition to turbulent, because of the Reynolds number. Okay, so Reynolds number, you know that as I say that rho v L in this case x. Okay, if you want to find out the position, so you can put x divided by mu. So x is the position. So if you consider x0 here, so Reynolds number is 0. But if you are the x value is very close, Reynolds number will be smaller, right? So again, if you are moving far, the x value will increase, so Reynolds number will also increase. So depending on the position, we will have the different Reynolds number. And if the Reynolds number is small, we have laminar. And if the Reynolds number is gradually increasing, we will have the transition. And if the Reynolds number is too high, we have the turbulent. So we can feel that the flow pattern is actually depending on the Reynolds number. And why we have the turbulent layer at the farthest end? Because the x is bigger and Reynolds number is higher. So at the beginning we will have the laminar region. Okay, then we have the transition zone, and then after that we have the turbulent zone. So here you can see the outer edge. This is the separation value, right? So here all the values above the line is already free stream velocity, right? And below it, of course, is less than the free stream velocity. It means we are experiencing the loss in the flow. So that I will explain later on. Okay, we have the loss in thickness, we have the loss in momentum, we have the loss in energy. So it's very difficult to consider these losses. Okay, if you are not focusing on this boundary layer, why we are studying this one? If you are not focusing on the boundary layer, you will not get into know the losses, and then you design the ships or any nozzle without considering this loss, then of course the delivery output will be of course less than you expect. Okay, so you always need to consider this loss and you need to add it, okay, with the design. Is very important, otherwise you will always face the loss, because is the theoretically is okay, you are getting this much flow, but you will not get the flow because there is a loss in the fluid flow, right? Because in this zone we don't have the flow that is equal to the u infinity, that is always less than the u infinity. So that's why it's very important to have the knowledge of boundary layer, and we need to consider these things in the design stage. Okay, so as I said, is why is 99.99. As I said that we define the boundary layer when the velocity reaches 99% of the free stream velocity, and the thickness is, we call this boundary layer thickness. Thickness of the boundary layer is the boundary layer thickness. Okay, and you can see that there is another thing is viscous sublayer, or we call this laminar sublayer. So laminar sublayer normally you can get in the turbulent zone. Okay, so there is an extra layer. Okay, so we will find an extra layer within the turbulence zone where the velocity profile is actually parabolic. Okay, there will be also a change in the velocity. So we have the change here, but inside the layer we also have another change. So that is the velocity. We call this laminar sublayer. The flow pattern, the velocity pattern is actually parabolic, but we consider is very small. The thickness is very small, so we consider it mostly linear. Okay, we call this the gradient is mostly linear. Gradient means, in this case I consider du by dy, right? Velocity gradient, whatever I say, the gradient means, velocity gradient means the change of the velocity along the distance from away from the wall means solid body. Okay, so these things you can use, these are all our synonyms, or we understand what you mean by these words. So it means that we call this is a linear. So that's why we call this, within the turbulent we have some zone where we consider the velocity change is very linear, so we call this laminar. So inside the turbulent we have laminar sublayer. Is a not layer, is a sublayer. And why is laminar? Because we consider the velocity change is linear, because it's very small. So we have this laminar sublayer. Okay, and then we have the buffer zone. Buffer zone is the zone. Okay, buffer zone is the zone where we have this laminar sublayer, we have viscous sublayer or laminar sublayer. Then we have some zone where we have the transition from the zone to the turbulent zone. Okay, so that zone, that buffer zone, is not belong to the laminar sublayer, is not belong to the turbulent zone. So that zone is buffer zone. We have the safety zone. Okay, that is the separation zone, what we can say. These things are already given in the slide later on, and these are the shear. These things I will explain later on. Okay, this is just briefly explain. Wall shear, it means wall shear means the stress at the wall shear. We have the shear stress. Okay, at different location, at different position, we have the shear stress. But when we consider the shear stress at the wall, it means wall means here. Okay, the layer that is attached with the solid surface or the wall, the shear at this level is the wall shear. We call this tau naught. We use the naught when we have the wall shear. So if we want to measure the shear stress, so laminar case, so normally is gradually reducing. We have the extra shear, but generally we overcome, and the turbulence, and we have the turbulent. Okay, so these are the wall shear profile. Okay, and you can see that the velocity gradient, so this one is explained here, is a 99% of u infinity. So that is, here is 99%, right? So that is the delta. In this case, delta is the boundary layer thickness. We use the delta for boundary layer thickness. Okay, so we have this, the things that I already explained is already there, so please read by yourself. Okay, so for an example, it said that the velocity gradient hence is shear stress, and the greater the wall decline as this proceeds into the fluid. So from this statement we may summarize that. What do you summarize? You focus here. The turbulence is 0 at the wall region, and the flow is laminar. Okay, so this thin layer close to the wall is called laminar sublayer. There is no turbulence there. and we consider the velocity profile is linear, so that's why we have laminar sublayer. And we have so shear stress decrease, okay, so and then you have the turbulence, so we have some buffer zone. This is the buffer layer. As one goes away from the wall, shear stress decreases and the turbulent activity appears. Okay, we have the gradually turbulence, so this is the transition we have. That is, we call this buffer layer. So it acts as a cushion between the sublayer and the main flow where the turbulence is fully active. So this is the thing, okay, so just read it, you will understand more. When I explain, I just explain very easily, and so that you can get the point, and then you can understand, read the notes, then of course they're right in a more concise way, okay, but sometimes it's very difficult. If you read, you will not understand, so I just explain in very simple words, okay. But it's better if you follow the wording. It should be like this, okay, then you will understand more. So basically you have to know the boundary layer thickness. Please note down. Sometimes you have the laminar sublayer and what is the buffer zone. Okay, so laminar sublayer within the turbulence. So within the laminar sublayer we don't have any turbulence activity. Okay, it's just behaving like laminar. There is no turbulence at all. And why we call laminar, I already said. You can also get more information if you just Google it. You can use YouTube if you want to know, you want to get more on it, so you can spend a little bit time, you will know the things, okay. So these are some extra things that I said. So what we summarize that when the Reynolds number is 5 to the power 5, we call this laminar. When the point is even is equal to or equivalent to like this, we call this transition. We call this critical value. Okay, the critical value means below it is a laminar and above it is a turbulent. Okay, so I don't know why someone is coming and leaving. I think the internet problem. So we have the turbulence boundary layer. So turbulent layer usually has a greater velocity gradient. These things you might find that I already mentioned. Okay, boundary layer we have. Okay, in case of laminar boundary, in case of laminar flow, we also have boundary layer. Transition, we also have boundary layer. Turbulence, turbulent flow, we also have the boundary layer. But when we have the turbulent layer, which means in case of turbulent flow, the boundary layer that we consider has a greater velocity gradient at the surface, which cause greater shear stress. So it means that if you have the change in the velocity is too much, okay, then we have the more shear stress. So it's common sense that in case of laminar flow you will experience less resistance. In case of turbulent flow you will have yeah, what is infinity? Hold on, you want to say what is infinity? What is infinity means u infinity. Where you find the infinity? It means u infinity means the free stream flow. There is no obstruction. U infinity. You can also use US. We call this like this. U infinity means the free stream flow. Okay, the flow is coming from infinity. It means the flow is coming from long distance and there is no interruption. So we call this free stream flow, and we represent in terms of US. Sometimes we use U infinity. Okay, that is the undisturbed flow, and it's coming from infinite distance. So this is the concept we use. Okay. Okay, so I just continue. So it means that in case of turbulent flow, we have the greater shear stress. It means we have the greater resistance. So similar way, when we have the ship and when it's flowing, I mean when it's sailing, so initially we need to overcome the frictional resistance. Okay, so it depends on the turbulence or vorticity. It's very important. Okay. So you will know about this vortex and turbulence, maybe friction resistance in the resistance and propulsion part. It's a different course. So, but I will explain like why we need to know these things. Okay. Okay. So from a turbulent layer, there is a more readily interexchange of particle. There is normal things, the information exchange. Okay, with the main flow, and this explains more rapid increase in the thickness of the turbulence. It means as I said that why we have the greater thickness in the turbulence layer. So it means that we have the velocity gradient is too much changing. Okay, u by del u by del y is higher in case of turbulence zone. So it means that the particle is actually exchanging its position. if it is exchanging its position, so it will take occupy a larger distance, okay, than if you compare with the laminar flow. Here also is occupying, it means the fluid particles are exchanging its position, but it's not like in turbulent phase. Okay, so in the velocity gradient is too much, it means the change is too much, the velocity particle is exchanging their position abruptly if you compare with the laminar one, and that's why it will actually increase the thickness of the boundary layer in the turbulent zone. Turbulent layer means boundary layer in turbulent zone. Okay, so the thickness of the laminar boundary layer is maybe, if it is times of 0.5, that I will explain, okay, in the next figure. We consider the pressure is uniform. If in case of turbulent, it should be times of 0.8. So what does it mean, 0.5 and 0.8? So this is the plot of a real fluid, the boundary layer. Okay, so this y by delta, so delta means the main thickness. Okay, so if this is the layer, this is delta, it means here your u is actually 9.99 u infinity. Okay, and in this case u is 0, right? So how this will change u and attain the 0.99% of this? So that is the thing is here. Now they use the um, sometimes they use u infinity. Okay, all are same, free stream velocity. So it means that attainment of the velocity, so at this point, if delta is equal to 1, it means its delta should be y is equal to delta, right? If y by delta is equal to 1, so it should be here u and um should be equal to 1. It means u will attain the maximum velocity. It's actually 0.99, but for simplicity they consider 1. So this should be 1 and 1, right? So the extreme level, it should be 1. It cannot be more than 1. So how it will attain? So this is, if you want to find out the velocity, so here 0.2, it means at when y is equal to 0.2 times of delta, it means 20% of the boundary layer thickness, the velocity will attain here. The velocity will attain maybe 0.35%. Okay, u, it means u will be 0.35 of mainstream velocity. Okay, but on the other hand, in case of turbulent, you can see at this position your this one attainment is u will be um is 80%. Okay, so 80%. Why? Because it's turbulent. The velocity gradient, the change in the velocity is higher, the change in the velocity is low. So that is the slope. Okay, so it means that in case of turbulent layer, the change in the velocity is higher, but it will occupy more, the thickness will be greater because it's the particle is exchanging its position. Okay, so remember that. Okay, so similar way, if you compare here, maybe 0.4, so when it's 0.4% of the velocity thickness, I mean the boundary layer thickness, so here is the laminar layer, it should be here. On the other hand, your turbulent is here. So you can see the change is gradually laminar. Okay, almost is linear. On the other hand, in case of turbulent, is like sharp change. Okay, there's a sharp change because the velocity gradient is higher, and change it take place not here, but suddenly it took place, and then it will exceed. You can see here is exceeding. It means the thickness is higher than the laminar layer. Is already attained here. Okay, so it means the velocity is already attained at this point. At this point is 1, right? It means the u is equal to already um at this point. So here is the thickness of the boundary layer. On the other hand, in case of turbulent layer, so it exceeding this one. So here, so it attained the value of the maximum velocity here. So we have this difference. Okay, so that's why we have the turbulent layer. We have the higher thickness because of the reason is because it's exchanging the position more rapidly. Okay, so you might have some guesses and you have some understanding, but it's very difficult to what can I say, visually show, right? So this one is just to read and try to understand. Okay, the last thing is the boundary layer and the potential flow or potential theories are used to define the drag component of the ship. So sometimes you might they will say, you might get questions that why we need to know the boundary layer and how you will utilize this knowledge, okay, when you consider the design of a ship. Okay, so mainly remember that, as I said, in case of ship, we have the resistance, right? We have to overcome the resistance, and in our case, we have to consider the frictional resistance. This frictional resistance is very important and is due to the shear stress, and shear stress is actually belongs to the boundary layer. Okay, if you have a thicker boundary layer, you will have more shear stress. We will have also the wave making. So wave making resistance we actually consider using potential flow. On the other hand, we consider the frictional resistance, we call it using we measure it using the shear stress, that is the boundary layer. Okay, so we have the two different components and we use the shear stress and the potential flow together to measure it. Okay, so will be equal to the component fluid. Okay, so it means that when we consider the shear stress, we are considering the force that is acting tangential to the fluid body, tangential to the ship body, and it must overcome to get the propulsion speed, right? So the resistance coefficient, this one you know or not, I don't know. We call this a resistance coefficient. So total resistance is a formula that we use. Later on, you can also you will learn it later on. Half rho v square s. Sorry, I don't have a space here. So rho is the water density, v is the velocity of the ship, s is the weighted surface area. It means the area that is below the water or immersed water. Okay, so if you use this formula, you will get the total resistance coefficients. But as I say, the resistance acting on the ship consists of friction due to the shear stress and wave making, which can be analyzed using the potential flow. Okay, so which are equal to the component of the fluid force acting parallel to the axis of the motion of the fluid of the ship. Okay, and also it said that for an adequate ship design, not only the pressure distribution around the hull and wave resistance have to be minimized, the desired value, but also wave pattern at aft body and axial tangential velocity. These are need to be measured. It means that you not only consider the pressure force here, but you also need to consider the wave making resistance, the wakes, and the tangential velocities, that is the shear stress. You have to measure it. So we design the F shape. Okay, so we have some renovation or innovation, as you can say, to minimize the drags, to minimize the tangential force, to decrease the friction resistance. Okay, so this can be considered during the initial stage of the design. So that's how we can consider the theories. We need to consider the boundary layers and the potential flow theories when we consider the ship resistance. Anyway, so now I will not extend the lectures, okay? And we have one problem that to solve, but I was told that you already know all these things. So let's try to solve this problem. Later on, from the next week, I will start the tutorial. Okay, not this week. Okay, so we have the problem is here. I think you have the knowledge of fluid 1, so you can solve it. Okay, by the way, let's stop.